Welcome to Maths with EJD. I'm still talking about numerical analysis. And now we switch gears and we start talking about numerical differentiation and integration. Come along and let's have a nice time with this. Okay, so of course, our objective here, the focus in the first place is numerical differentiation in this video, and it's numerical differentiation using finite differences. And the objective of numerical differentiation is to approximate. Okay, I guess we can even um, overview. I mean, that's a kind of overview of what this is about, right? Um, our objective here for talking about numerical differentiation using finite differences, the objective of numerical differentiation. I'll just squeeze that in. Yeah, it's got it. So the objective of numerical differentiation is to approximate, the derivative of a function at a given point using discrete data. So we can even talk about derivative with even data when where we don't really have a particular function in mind. So this method is particularly useful, is particularly useful when functions explicit form, when functions explicit form is unknown, or when data points are given rather than the actual function. Okay. So the finite difference method provides an effective approach for approximating derivatives. Okay, that said, let's look at some basic concepts of finite difference. Basic concepts. So the derivative of a function f of x at a point x naught is defined as the limit f prime of x naught equals limit as delta x approaches 0 for f of x naught plus delta x, f of x naught plus delta x minus f of x naught, all divided by delta x. Of course, as delta x approaches 0, like I said earlier. So this is the definition, numerical definition of derivative. Now, that said, that's the definition, non-numerical, sorry. That's just the definition, first of all. So, however, in numerical differentiation, we approximate this limit. We approximate this limit using finite differences. Finite differences. And in that, what we do is we use a small value h, a small value h, which is known as a step size, instead of taking the limit, because we probably do not have a particular function we can hold on to, but we have data points. So let's talk about types of finite differences. Types of finite differences. So as we talk about the types, we take examples. So the first type is what you call the forward difference. Forward difference. Okay, you have the forward difference. So the forward difference formula, approximates the derivative at x naught using the function values, at x naught and x naught plus h. That's why it's called forward difference. So you go, so you start from x naught and move a step ahead, right? So here the formula is f prime of x naught is approximately f of x naught plus h minus f of x naught all over h. So we have all this. Okay, so that goes. Let's take an example of this then. Example for forward difference. So we say let f of x be equal to x squared, and we want to approximate f prime of 1. Of course, you know f prime of, I mean, x squared is simple, but it will help us understand easily. So if f of x is x squared, so f prime of x is 2x. So we know f prime of 1 should be 2, simply, right? So we know that up front. And we want to approximate f prime of 1 using a step size h equals 0.1. Okay, so in that case, what we simply have would be f prime of 1 is approximately, from the principle, right? We have f of x naught plus h minus f of x naught all over h. So we just have f of x naught, okay, um, we need to refer to the formula, right? But I don't have to write. F prime of x naught equals approximately f of x naught plus h minus f of x naught divided by h. So in here we are taking 1 as our x naught, although that is not explicitly stated. So let's take it that, or let me just say, let x naught be equal to 1. So we know h also. We already know h to be 0.1. So if x naught is equal to 1, then we can now say that f prime of 1 is approximately f of 1 plus 0.1 is x naught plus h now, minus f of x naught, which is 1, all over h, which is 0.1. So if we work with this, so f prime of 1 is approximately f of 1.1 minus f of 1 divided by 0.1. So if we go on with that, so f prime of 1 is approximately f of 1. F of 1.1 is simply, f of x is x squared, right? So it means we have 1.1 squared minus 1 squared all over 0.1. That's what that is going to be. So, so it's f prime, sorry. Hope I've not forgotten. Yeah, f prime of 1 is approximately 1.1 squared is simply 1.21. It's simply 1.21 minus 1 all over 0.1. So all this over 0.1. So, and then we have f prime of 1 to be approximately 1.21 minus 1. That is 0.21 divided by 0.1. So, we simply know that's 2.1 all over 1, which is 2.1. So we get that easily. So we have 2.1 right there. So we can say therefore f prime of 1 is approximately 2.1. Settled. So we know that the true value of the derivative, like I said before, is f prime of x, which is equal to 2x. So we know that f prime of 1 is simply 2. So the approximation 2.1, the approximation 2.1 is close, it's actually close to the true value, but introduces a small error, okay? So that is forward difference like that. Then we move on to the next one. That's backward difference. The second type of finite difference is what we call the backward difference. So here, the backward difference formula uses the values at x naught, and then because it's backward, right, it goes a step backwards. That's x naught minus h. The other one is x naught plus h. All right. So here it's x naught and x naught, x naught and x naught plus h. Here it's x naught and x naught minus h. Okay. So the backward difference formula uses the values at x naught and x naught minus h to approximate the derivative. And in that case, we have f prime of x naught, which is approximately f of x naught minus f of x naught minus h all over h now. So since most likely these are just numerical values, we are not able to guarantee taking the limit. So we are going, in case you have just data points, you could just be given values, and then you have to find the numerical differentiation. So we can do all of this. Okay, so with this now, with this backward difference case, we need to take an example. Imagine that we have the same example. So for the same function, f of x equals x squared. So again, we want to approximate f prime of 1 using same h equals 0.1. So we just have f prime. Okay, let me switch over now to save this. So we have f prime of 1. F prime of 1 is approximately f of 1 minus f of 1 minus 0.1 divided by 0.1, which is h. So that means we have f prime of 1 approximately f of 1 minus f of 0.9, I believe, all over 0.1. But we know f of x is x squared, right? So we have f prime of 1 approximately 1 raised to power 2, that's x squared, then 0.9 raised to power 2, that's x squared, divided by 0.1, so that f prime of 1 in this case is approximately 1 minus 0.81, I believe. That's 9 times 9, 81, two decimal places, divided by 0.1. And then we have f prime of 1, which is approximately 1 minus 0.1. Just imagine it as 100 minus 81, that's 19. So we have 0.19 divided by 0.1, and that is equal to 1.9 divided by 1. If you shift the decimals by one step, so the answer is 1.9. Okay, so we can say therefore f prime of 1 in this case is approximately 1.9. So it's close to 2, right? But it has shifted a bit backwards. So we can say that we know the true derivative already. The true derivative at x equals 1 is 2. We know that because f of x is x squared, so f prime of x is 2x. If you put 1, you just get 2, right? So the approximation is a bit off. I mean, it's 0.1 short of the reality, but I mean, it's pretty close for sure. So we have that. Then from there, we move on to the next one. That we are talking about types of difference. We've talked about forward difference, we've talked about backward difference. Then now we're moving on to the next type of difference, which is called the central difference. Central difference. So don't forget, the forward difference, we got 2.1. Backward difference, we got 1, we got 1.9. So central difference, let's see what happens here. So the central difference method uses both the forward and backward differences, both the forward and backward differences to calculate a more accurate approximation, okay, by considering values at x naught plus h and x naught minus h. Okay, so that we now have our formula to be f prime of x naught is approximately f of x naught plus h minus f of x naught minus h all over 2h, So it's more like we have one step ahead, one step behind. So at the end of the day, we have two steps altogether. So for forward difference, we had one step ahead. For backward difference, we had one step behind. But for central difference, we have one step ahead, two steps behind, and one step behind, meaning that we have two steps altogether off the center. So that's why this is now divided by 2h. So if we take the same example we've been taking, say, example again, same thing. So we want to approximate f prime of 1 for same f of x, which is x squared. F of x equals x squared with h equals 0.1. Okay, this one here is why we have x naught rather, actually. So with this now, we can just go straight since we've been doing this a lot. So we have f prime of 1 is approximately f of 1 plus 0.1 minus f of 1 minus 0.1 divided by 2 into 0.1. Okay, that's what we have. So f prime of 1 is approximately f of 1.1 minus f of 0.9 for sure, all over 0.2 down here, so that f prime of 1 is approximately 1.1 squared minus 0.9 squared, because f of x is x squared, so f of 1.1 is 1.1 squared. So just like f of 0.9 will be 0.9 squared. So we have f prime of 1 is approximately 1.21 minus 0.81 divided by 0.2. And if you try that out, you have I think that should be 0.4, right? At 1.2 minus 1.21 minus 0.81 is 0.4. So we have f prime of 1 to be approximately, is even approximate. It's actually In this case, it's in this case, okay, well, not a problem. Let's just go on. So this is simply 0.4 divided by 0.2. So, I mean, with all finality, I mean, this is equal to 0. This is equal, if you shift the decimal back behind, that's just 4/2, one decimal place. So, and that the answer is 2. So you can say, therefore, f prime of 1 is equal to 2. And that's how it goes. Okay? F prime of 1 is equal to 2. So you see, in this case, the result is on point. So we can say that this result matches the true value of f prime of 1, which is actually equal to 2, showing that the central difference method provides a more accurate estimate, Okay. So, I mean, so if you have to choose an option of all the types of differences, um, you know, that the central difference is the best for sure. So we have now the next thing is we're talking about error analysis. So we can see there's the one in numerical analysis, right? Error is one of the key things we have to talk about. So the accuracy of numerical differentiation, the accuracy of numerical differentiation, the accuracy of numerical differentiation depends on the step size, h. Okay. So first of all, we have for forward difference. So you see the error term is of order big O of h, meaning the error decreases linearly. The error decreases linearly as h gets smaller. So the smaller h is, the better your result is going to be. So next you have for backward difference now. Backward difference. So for backward difference, similar to the forward difference, the error is also the same. The error is also big O of h. So as the value gets smaller, the error decreases linearly. Then we have central difference, which performs better than the previous two, right? You have the central difference. So you expect the error to reduce faster. So the error term is of order big O of h squared, meaning the error decreases quadratically. Error decreases quadratically as h gets smaller, making it more accurate. Than the forward or backward methods. Okay. So we can actually reach a conclusion. Okay. So numerical differentiation using finite differences, using finite differences is a powerful tool, is a powerful tool for approximating derivatives, approximating derivatives when analytical solutions, when analytical solutions, when analytical solutions are difficult or impossible, difficult or impossible. I mean, the example we used is it's not important, it's not difficult actually, but we needed to use that to assure ourselves that it is a nice method to go for. So by selecting, so in that case now, if you are not going to have a function like that, yeah, you probably just have a table, and then you are required to differentiate, right? So by selecting the appropriate method, by selecting the appropriate method, um, by selecting the appropriate method, okay, and step size, method and step size, very important. By selecting the appropriate method and step size, one can obtain accurate approximations for the derivative for the derivative of a function based on discrete data, And finally, the central difference method, is particularly advantageous due to its higher accuracy, And like I always like to do, I like to show you the Python implementation of almost everything. So here, this is the Python implementation for this. And so here, so we have the function x squared, which we are trying to work on. So if you have another function, you can define it there. So you have that function, and then you define forward difference, backward difference, central difference as functions, and then the true derivative is here as 2x. So whatever you have here, you also have to do the true derivative here. So then you have your x naught, which is 1. That's the point at which to approximate the derivative. That is 1. So I didn't have to worry about x naught the other time when I did that when I was working. So the point you're evaluating is automatically your x naught, and then you have the forward difference, backward difference, and all of these things. So okay, I mean, it's even implemented already. So if I clear this out now and retry, okay, so you get, so we have, by the time, so forward difference gives 2.1 something something, backward difference gives 1.89999. So you can see this is even more accurate. Central difference does not actually give the exact 2, but it gives 2 point something something. So it's very close to 2. And then you have all the errors. So the biggest error is from the backward difference. If you look at these values, I mean, it's from forward difference. The smallest error is from central difference, just like you saw already. So, I mean, that's how all of that goes. And that is the idea of numerical differentiation with forward difference. Let me see if I'm able to quickly come up with a table because it's actually used for discrete data. Okay. Okay. Table for what's that thing now? For difference method, right? Finite difference method. Is the approximation now? Finite difference method. Numerical differentiation. Numerical differentiation. Okay. So let's see if that works, and then I can make that into an example. Okay. Okay. I think that's not working. Okay, I mean, so what we currently have is fine. What we currently have is fine. Let's not. Okay, well, I can do something. I can actually do something. So let's assume that mm, okay, let's do this. Practice question, right? Practice question. Practice question. Because this is the proper thing this is meant for. Imagine that you have you have you have x and you have f of x. Okay. So, and this is, so your x, when x is 1.9, you have 3.61. Then when x is 2.0, you have 4.00. Okay. And when x is 2.1, you have 4.41. Okay. So now you want to compute. So the issue is you need to the question is to approximate the derivative at x equals 2 using forward, backward, and central difference methods. With h equals 0.1. Okay, so your x naught is already 2, so you can just do that. So you don't, if you, in case you have a table and you don't even know what the function looks like, and this is just all you have, so that is exactly what numerical differentiation is meant for. So let me see your answer in the comment section, if you would do this, and then of course feel free to let me know how helpful these videos are, and let me also know if there's a topic you'd like to teach or a problem you'd like me to solve. And of course, if you have subscribed, thank you. If you have not, go ahead and do that right now, because there's still so much to learn. And of course, also hit the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. In the next video, I'll be talking about difference operators, which are also connected to finite difference. But that one, there's not so much of numerical. We are just going to see some relationships and some beautiful expressions for these things. Till I come your way again, keep doing maths right. Bye.